Okay. Our next speaker is David. So his topic is actually a bit similar to mine. So it's about pre-training as well, but this time in the computer vision domain. So the main topic is to pre-train from the pixels without the 2D information, the structural information, and they want to see like what they can do with it. So without further ado, let's welcome David.
Thank you, Eric. Okay. So, like Eric said, my paper is similar to his, and it's rather than language, we'll be looking at images, so pixels. So, today I'll be talking about generative pre-training from pixels. First of all, I'd like to apologize. I prepared a 15-minute talk instead of a 30-minute one, so this might be a lot shorter than Eric's. Anyway, so here's a quick outline of our presentation. I'm not going to discuss it. So unsupervised pre-training is a method where a model pre-trains with unlabeled data and fine-tunes with supervision. So it plays a central role in the resurgence of deep learning with approaches such as deep belief networks and denoising autoencoders or DAEs. It was believed that a model that learned distribution PX would learn beneficial features for the subsequent supervised modeling PY given X. However, pre-training fell out of favor in computer vision. State-of-the-art relied directly encoding prior structures into the models. Some studies cast doubt on the benefits of pre-training with computer vision. Some even found it harmful in modern settings. And self-supervised approaches were showing promise compared to supervised methods. So attention shifted from pre-training to self-supervised approaches. However, of course, pre-training didn't really disappear. It flourished in natural language processing. Here we have the benchmark scores for the GLUE benchmark. Use some sort of pre-training, usually transformers, or as you can see here, like Eric discussed, you have Bert, Ernie. We also have, we have lots of variations of Bert. So pre-training flourished in NLP. As Eric discussed, what BERT does for pre-training is it masks the original input, then it attempts to recover that. So that's how it pre-trains itself. So that is actually similar to what DAEs do. So they take an input, they corrupt the input, or in the case of BERT, they mask the input. Then they attempt to recover their original input. So for this paper, the goal is to reevaluate the generative pre-training on images, to compare it with self-supervised methods, to evaluate in different data sets and evaluation settings, and to experiment on model performance with respect to and other parameters. So for the approach, we're going to talk about how pre-training works, the evaluation, and the architecture. So this is a brief summary. So for number one is, of course, pre-processing. The first step is to lower the image resolution to something more manageable. Then it's converted to a 1D vector of pixels because the following methods will use one-directional vectors. So for pre-training objectives, they use two objectives here. First is autoregressive. The second is BERT. So for autoregression, the goal is to predict the next pixel here. So this is your input, then your goal is to predict the next one. And these are the details. The goal is to minimize this equation. For BERT, the goal is to recover the masked pixels. So these are the masked pixels, then you want to recover them. So for BERT, they want to minimize this equation here. Chances of being masked is 15%, by the way. So 15% of the pixels input are masked. Then after that, we evaluate using either linear probing or fine tuning. For linear probing, the average pool on individual layers, I believe. So for each layer, they take it. For fine tuning, the average pool across all the layers. Then FL is used to classify the logits and minimize the loss function. For the architecture, what's fascinating here is they actually used the GPT transformer block, which is actually from natural language processing. So they didn't change it in any way. They just copied it, and that's what they use for the architecture here. So from NLP to images. Then for auto-regression, they applied a standard upper triangular matrix to the logit matrix. They also ordered the raster. The raster ordered for to specify the ordering of conditionals. But for BERT, they didn't do any of those things. Let's talk about the methodology. So first, the dataset, the context reduction, the models, and the training. So similar to Eric's paper, they use several datasets. The largest one being ImageNet here. So they use ImageNet as an unlabeled dataset to pre-train on. ImageNet has labels, but for pre-training, they just ignored the labels there. Then they have these three datasets, C410, 100, and STL10. Then that's where they use their labels for fine-tuning and yung isa pa nga. For context reduction, the memory requirement of transformer decoders scales quadratically with context length. So it's important for the research to reduce that context. So the first obvious reduction is in input resolution. So they reduced it to 32 by 32, 48, 96, and 192. With the smaller resolutions, they also reduced it further by clustering the RGB using k-means. So instead of having 3 color channels RGB, they reduce it to 1. For the higher resolutions, they reduced it using something called vector quantization. Like Eric discussed, we have it discretizes the input. It reduces the size dramatically. So they also had 3 models to work with. IGBT-L, medium and small, large, medium, and small. So they wanted to see the effect of model capacity. And they also varied the embedding sizes. They actually had another model, extra large, pero hindi na nila sinama sa paper. Finally, some training details. They used the batch size 128, 1 million iterations using Adam with these betas. Different learning rates, 0.01 until they found a local minimum. Then they used 1 epoch. Then no dropout was used. Further details, for fine-tuning, they used the same batch size and Adam hyperparameters, still no dropout. When linear probing on ImageNet, they use these methods. And on other datasets, they use this algorithm for consistency with other results. So let's talk about those results. So they actually answered 7 questions here. So that's 1, 2, 3, 4, 5, 6, 7. But before we explore that, let's see some examples. So here are some sample images. These are the input images. And these are the completed images by the model. And these are the original images. So it's personally, I find it fascinating. Look at the detail here. The cat actually has paws to hold stuff with. Okay. So the first question was, what representation works best in a generative model without latent variables? So unlike supervised learning, where the best performance is usually at the last layer, for unsupervised pre-training, it's actually found around in the middle here. The performance increases as we go deeper, but once we reach somewhere around the middle, the performance actually decreases a bit. So this suggests that the model is two-phased. The first phase is creating a global image representation. Then the second phase uses that representation to solve different tasks. The next question is, intuitively we know that bigger models would perform better, and that's what they found out. So they used they found that larger models, large, medium, small, so green, orange, and blue, perform better and over uh, improved performance with they found improved performance with improved representation quality. So here we have reduced validation loss here. So the lower the validation loss, the steeper the increase in performance. The larger the model, the higher that performance is. So exploring linear probes on CFAR and STL10. So remember that the model was pre-trained on ImageNet, and they evaluated on other data sets to see if the model is useful across different data sets. And as you can see here, the model actually performs very well. AMDIML is self-supervised then, while RESTnet is actually pre-trained with labels. Here, for SCL10, despite having a lower input resolution than AMDIM, IGPT actually outperforms it by a small margin. Next, exploring linear probes on ImageNet. They arrive at two conjectures. First is that training on longer contexts or larger modular resolutions will yield the largest improvement in linear probe accuracy. So here we have different input resolutions, and the higher we go, the higher the accuracy we get. Then finally, we have features from wider models will outperform concatenated layer-wise features. So for full fine-tuning, compared to GPipe, which uses supervised ImageNet transfer, IGPTL actually ties it for CFAR 10. And for CFAR 100, it's still competitive with AutoAugment and EfficientNet. Which EfficientNet, by the way, is actually supervised, but IGPTL is unsupervised. GPipe is supervised, IGPTL is unsupervised. For BERT, initially it performs poorer than auto regression. So as you can see here, BERT has this initial performance, and AR has this initial, then AR has this. But after fine-tuning, BERT tends to outperform or at least reach up to AR. So here is the improved performance of BERT, and this is for AR. It's a very small difference. In ImageNet, BERT actually outperforms AR. And if they can actually boost it even more by using ensembling masks. For low data CFAR 10 classification, so they wanted to explore how the model would perform when given low data image processing. So using limited labels. So using limited labels, 40 labels, they find that their models are performing well enough. So let's see some related work. First is the Big by GAN. It's an unsupervised learning approach based on generative models. It is a bidirectional GAN with big GAN generators, big implying scale. It achieves state-of-the-art performance in image representation when trained on ImageNet. It's also competitive with supervised and unsupervised, self-supervised models. Another related paper is contrast predictive coding. This one utilizes the autoregressive prediction objective. Like BERT, it is also domain agnostic. So it can also be applied to audio, to visualization, text. Here's a quote from this paper. Contrastive methods are the most computationally efficient methods for producing high quality features from images. And CPC actually improves upon the state of the art. Finally, we have SIM-CLR, another contrastive method. SIM-CLR stands for Simple Model for Contrastive Learning Representation. It uses a non-linear head at the end of the network. It outperforms AlexNet with 100 times fewer labels. So finally, we have some discussions and conclusions. The results suggest that generative image modeling is still a promising route to learn high-quality high-quality unsupervised image representations. In cases of low-resolution settings, GPT for pixels achieves state-of-the-art performance. In high-resolution settings, it's at least competitive with self-supervised methods. So some potential future studies, they want to eventually bridge the model to use higher resolution images. Uh, they also want to explore some architectural changes because it's computationally expensive. It scales quadratically, so that's not good. And finally, they also want to explore other generative models such as VAEs and flows. And that's it. Thank you.
Thank you, David. The floor is now open for questions.
Hi, David. I have a question.
Go ahead.
Okay. Tama ba na based on my based on my understanding, did their model not use any form of convolutional neural networks? More of yung NLP models yung ginamit nila?
Yes, alam ko ginamit lang talaga nila was yung yung architecture was yung based lang din sa ito, galing lang din sa GPT-2.
Okay. Yung sa kasi I'm looking at the figure in their paper and they said the first step that they did was to pre-process raw images by resizing to a low resolution.
Yes.
And reshaping it into a 1D sequence. So
Yes.
yung part na resizing na yun, is that like did they use a network for that or more of yung mga other techniques lang like by linear interpolation, yung as in resize lang talaga siya?
Actually, hindi ko nabasa if may specific na method silang sinabi. I think linear interpolation lang talaga yung ginawa nila.
Okay. So, interesting kasi I guess what interests me here is that normally when we think of images, yung what we think of first is that normally CNNs talaga yung ginagamit. So I think this is an interesting study kasi they use parang models that were originally designed for NLP problems.
Yes.
To solve problems which we normally address using CNN. So I guess my last question would be parang what do you think is the implication of this study regarding dun sa thinking na CNNs are the way to go when it comes to solving computer vision problems, yung mga images involving images?
So, pre-training actually, ginamit na siya sa images before pa, pero ayun nga, na-outperform siya ng CNNs. So, I guess this means na just because na meron ng ibang leading doesn't mean you can't explore other methods. Personally, natuwa nga ako na, it excelled in NLP and we found that it can actually perform well then in images. So that should make us think baka yung ibang networks pala mas useful din sa ibang fields, di lang natin alam.
Okay.
Did they say, sorry.
Yes, Ate Mabel.
Did they say how much computing power they have? Because this is GPT. GPT kasi siya. So, lahat ng GPT, yung number of hyperparameters is masyado talagang madami.
Ang pinakamaliit actually na parameters nila was like 74 million.
Yun nga.
Tapos yung pinakamalaki was 1.4. Based sa paper,
yung latest nila na GPT is mga ilang libo yung kailangan mong gastusin ng per run. So, I'm just curious, did they mention any form of downsizing from the GPT model for this to be effective for repurposing, for example?
Wala sila na mention na downsizing. Actually, na-point out nga nila na medyo hindi siya compact compared sa ibang methods. Kaya, ang ginamit nila dito was 1024 tensor processing unit cores I'm not sure how big that is, but it sounds like a lot. By the way, this paper was presented by the OpenAI team pala.
Yeah. Sila naman yung may research ng GPT. So.
Yeah.
Raf, may question din ako.
Yes, Jesse.
Quick lang. So, itong GPT na transformer na model, ano siya? Trained from scratch siya? Wala siya nung NLP parang existing na weights?
Alam ko, wait, let me check on that. Pero alam ko from scratch talaga siya eh. Wala sila na-mention na existing weights or anything. Yeah, wala silang na-mention existing weights.
Thanks.
Does anyone have any more questions for me? Hello?
Hello? May iba pang questions?
So from a research perspective, anong balak mong gawin or i-take from this paper for your work?
Oh, I'm actually not sure, Ate Mabel. Definitely, I want to explore computer vision. I'm wondering if ma-apply to in engineering context na parang you can auto-complete some problem na hindi clear sa engineers. So, but I'm not sure yet.
Okay. So context-based din kasi yung ganong klaseng problem, di ba? So
Yes.
baka mahirap din siya. Pero yung ganitong klase ng usage kasi usually parang generalized. So for yung applications nila, you may need to look for a good usage kung gustong much more specific. Okay.
Thank you, Ate Mabel.
Okay.
Any more questions?
Sorry,
I guess not. So,
sharing.
thank you, David, for your talk. Very enlightening, interesting.